Hi everybody, let's do this algebraically finding limits of function at undefined values. You know, undefined values, when you have a number over 0, that's undefined. And if you guys remember the steps from the previous video, it was the first one. You plug in, I'm just going to write them one more time. You plug in, if you get 0 over 0, you need more work. I'm not writing the whole sentence. Need more work. What is that more work? You factoring top and bottom. You have least common denominator. You do conjugate if you have square roots. And you do distributive property like a foiling, distributive property. Or you just open it at expand. That's another one. You expand the equation or something. Second, if you plug in and you get number over 0, then it means it's undefined. Your answer has to be positive, negative, infinity, or does not exist. Okay, and you're gonna pick arbitrarily close number, and you're gonna plug that in again. Arbitrarily closed number, you're gonna plug it in again. Then you're gonna look for, look for signs, not numbers, signs, because we already know our answer is positive, negative, infinity, or does not exist. So we look for signs. If I have positive, then it means I have a positive infinity. If I have positive, negative, then it means I have negative infinity. If I have negative and negative, you know it's a positive infinity because they cancel out each other, right? Like that. So that's what the steps are. So let's do this. What happens if we try to evaluate this limits below by the direct substitution method that was used in the previous 6 examples? This is the previous video I'm talking about. So if this is what it is, I'm going to plug in, I'm going to do direct substitution here. When I do direct substitution here, limit x approaches -3. So it's going to give me -3 squared plus 4, -3 plus 3 over -3 squared plus 2x minus 3. Now you have to be very careful about plugging in -3. Okay, -3 whole square and -3 square, these are completely two different things. Okay, since I'm approaching -3, so -3, the square 2 up there on the top is going to go on the whole term, negative and 3 both. Not like this. This means the 2 is applying only on 3, not on negative. So this is what it is. When you, okay, this one was -3. When you solve this whole thing, I know I'm getting 9 minus 12 plus 3 over 9 minus 6 minus 3, and it means 0 over 0. You see that? That's what I mean by 0 over 0. If it's 0, 0, then we need more work. I'm not solving the problem next. I'm just gonna plug in and see how it's going. Then we're gonna answer the question using graph, and then we will do it after that using all that stuff. But this is 0 over 0, right? 0 over 0 means you need more work factoring. This one is going to work factoring because it's a quadratic equation, both of them on top and bottom. Let's try plug in 1 in here. If I plug in 1, I know I'm getting 1 squared plus 4 1 plus 3 over 1 squared plus 2 1 minus 3. And the question is going to give me 8 over 0. That's undefined. Do you see? I didn't even pay attention the left and right. Do you guys see this? This is right, that's a left, but I just plugged in directly. This is the first thing you should do. 8 over 0. If I get 8 over 0, it means I'm going to pick arbitrarily close of 1 from the left. I'm going to pick arbitrarily close of 1 from the right. Plug in and we'll decide what our answer is, positive, negative, infinity, or something else. So, but this is what it is, okay? So we got undefined, and this is the one we're talking about today. So let's answer this question using a graph. Just because a function is undefined at the value of x doesn't mean that a conclusion cannot be reached about the limit. Consider the rational function above. From the graph of the function pictured to the right, what is the value of each limit below? So I'm using a graph, and I make these x-axis and y-axis and x-axis pink so we can easily understand. Limit x approaches -3 of this function. The graph is right there for the function, so I'm using a graph for -3. And if you guys closely pay attention, right there is my -3. I'm approaching left and right because they're not mentioning anything up here, any sign. So limit x approaches -3 from the left, and you see I have a hole on -3, so I'm going arbitrarily close right there. And I'm approaching -3 from the right, arbitrarily close. And you know the y value for this is right there. I can say that's half. That's 1 and that's half. I mean, not exactly, I can see it, but it's half. Now let's see, limit x approaches 1 from the left. This is my 1 and I'm approaching left. This is the left side of the 1. And when I approach this graph, you know I'm going all the way back there, like right there. There is nothing there, which means I'm going -infinity. There is no y value for 1. So this is -infinity. Let's try limit x approaches 1 from the right. So if you guys pay attention, 1 from the right, this is 1. I'm going graph 1 and it's going up there. It's not crossing the vertical asymptote at 1, but it's gonna go all the way up there. So it's a +infinity, because on this side the y values are all positive. Up here the y values were all negative. That's why it's -infinity. Okay, so we got it from the graph. Let's see. The task now is to determine how to find these limits analytically. How was it when we found the discontinuities of a rational function in pre-calculus? Okay, discontinuity. Now you have to be very careful. First part, if you get number over 0, which means it's undefined, that's a discontinuity, a hole, or maybe vertical, horizontal asymptotes. How do we know without the graph in the function that we have a hole or we have a vertical or horizontal asymptote? So let's figure it out, okay? Number 1, you factored, this is in pre-calculus we did, factored the numerator and denominator. That's the first thing. If you guys remember, I said plug in first. When you get number over 0 or 0 over 0, then you need more work, then you factor out. Second, if a factor cancelled, the function had a point of discontinuity, which means they said if a factor cancelled, this means a point of discontinuity. What kind of point of discontinuity? Because we have two different types of discontinuities. Like you have a jump, like a vertical, horizontal asymptotes, or you have a hole right there. Okay, so which one? This one is going to be a hole. Third, if a factor did not cancel, if a factor did not cancel from the denominator, then the function had a vertical asymptote. Okay, so if we factor numerator and denominator, if we cancel some factors, then it's a hole. If we do not factor anything in the denominator, then that's a vertical asymptote. Okay, let's figure it out. Let's apply all of that. We will perform the same algebraic analysis to find the limit of removable point discontinuities. Removable point discontinuity. Removable means a hole. Discontinuity, you know, it's a hole I'm talking about. Okay, so this is the question. what I do, I'm gonna plug in -3, which we already did on the top, and we got 0 over 0. So we need more work. I'm gonna factor because it's a quadratic, so let's factor out. I'm gonna write limit, and that's exactly how you do on free response questions, the way I'm doing it. You're gonna plug it in, you will show them right there, that's 0 over 0, then you're gonna start working exactly the way I'm doing it, guys. -3, and I'm factoring out x plus 3 and x plus 1 right there. If you don't know how to factor, please watch my algebra 2 videos so you can refresh everything. This is x plus 3, x plus 1. Again, in the bottom, I have x plus 3 and x minus 1. X plus 3 and x minus 1. If you see the factoring, I'll just show you for this one. You have 2 x's and you have 3 and 1. The factor of 3 is 3 and 1. And if I subtract 1 from 3, I get 2. Or you're going to get something like you add 3 and 1 and you get 4. You see that? So 3, 1 works. That's how this is going to work. If you have both positives, then you have a positive everywhere. If you have one positive, one negative, then it's one positive, one negative. But if you have a negative in the front, in the quadratic function, or anything you're factoring, any function you're factoring, if you have negative in the front, like negative and positive, then both of these factors are going to be negative. That's something like a quick tip. Now, if you see, I'm canceling x plus 3, x plus 3. Okay, so what is left? Limit x approaches -3, I got x plus 1 and I got x minus 1. Plug in that -3 one more time. So that would be -3 plus 1, -3 minus 1, which will give me -2 over -4. And the answer is positive half. That's how you solve when you get 0 over 0. You factor them, you cancel them, and then you plug in again, and then you will see the answer. That's why we need more work, because if I don't do this, don't cancel this, then if I plug in -3 one more time, it's going to give me 0 over 0. So that's why we need more work to get the answer. Let's try this. Based on our knowledge from pre-calculus, we know if rational function has non-removable infinite discontinuity graphically, a vertical asymptote exists. A vertical asymptote exists. Since the y value do not approach one specific value from both sides at a vertical asymptote, then the limit does not exist. However, we can determine if the one-side limit approach -infinity or +infinity. In order to do this analytically, we will marry the numerical, graphical, and algebraic approaches. For each limit below, determine the sign of simplified function at the value to the right or left of x equal 1. Okay, this is what I'm talking about, guys, up here. And by the way, let me go back to this question. And we will go in detail, but let me show you this. Do you see I cancel x plus 3, x plus 3? So I'm just going to do it here. X plus 3 equals 0 will give me x equal -3, right? So you have a hole at, you have a hole at -3. When you cancel something out, do you see if a factor canceled, the function had a point of discontinuity, and that point of discontinuity was a hole. So you have a hole at x equal -3. And if you check the graph back there, do you see this is -3 and you have a hole there? So that's what it means. Okay, what is left? Do you see in the bottom you have x minus 1? This x plus 1, x minus 1, I can cancel it. But whatever you have in the denominator, x minus 1 equals 0, whatever is left over, and it means I have a vertical asymptote at x equal 1. Vertical asymptote. Now, what did we know? How do we know this? You have x equal -3. Cancellation is going to give you a hole. I'm just going to write that. Cancellation going to give you a hole. Whatever is left in the denominator, you make the denominator equals 0. It's going to give me vertical asymptote. Now look at this. I have a vertical asymptote right there, and it's x equal 1. So that's what it means, but we're gonna go do it in detail. Okay, let's try this. Now, x approaches 1, and you remember we did this in the on the top, and we got number over 0, like it was 8 over 0 something. When I did this the first time, right there, 8 over 0, when you plug in 1. So I'm using these steps, okay? Plug in, we plugged in directly, we got the number over 0, not that one. So the answer is positive, negative, infinity doesn't exist. We're gonna pick arbitrarily close and plug them again. So this is what we are doing. If I get number over 0, I'm picking arbitrarily close of 1. Do you see this is a number line? This is positive 1, and that's a 0, for example. That's positive 1. If I'm going left of 1, this is left of 1. What is arbitrarily close up here? This arbitrarily close means I have 0.9, 0.0009, 0.9, whatever you want to pick, but you know this is 0.9 from the left. So I picked 0.9 arbitrarily close, and I'm going to plug in that arbitrarily close in there. So 0.9 plus 1, 0.9 minus 1. Now, if you check back my step, the steps that we have, you pick arbitrarily close number, plug it in again, look for signs. Like I said that before, we are not interested in numbers, just the signs, okay? So look at this. This is what I got, 0.9 plus 1. You know 0.9 is small number, plus 1 is bigger number. So when I add these two, no matter what, I'm going to get positive answer. I'm not, like I said, I don't need numbers. 0.9 subtract 1, 1 is a bigger number, it has a minus, so it means my answer up here is supposed to be negative, right? So positive and negative is going to give me negative infinity. We already know when we get this, we know the answer is positive, negative infinity. But how do we decide about the positive infinity or the negative? That's what we do. We plug in arbitrarily close and get the signs. Okay, this is 1 approaches, this is 1, that's 0. So if I'm approaching 1 from the right, this is right side. So arbitrarily close is right there by 1. It's going to be 1.1 or 1.0001, whatever you want to pick. I picked 1.1. So 1.1 plus 1, 1.1 minus 1. This one is going to give me positive, we know that. This one is going to give me positive because 1.1 is bigger than 1. So this one is also going to give me positive. So my answer is positive infinity. Okay, so if the question was asking, okay, what is the limit x approaches 1? Like they don't mention left and right because I already got left and right anyway. Does not exist, right? First of all, infinity means a not real number, doesn't exist. But since I'm getting left and right, 1 is negative infinity, 1 is positive infinity, I can say it does not exist. Okay, for limit x approaches 1. I didn't mention left and right because if they don't mention left and right and you still get number over 0, then you have to give them left and right limits. Otherwise, it's not going to work. And then I have f of x, whatever that function was, does not exist. And why? Because limit from the left and right are not equal. Okay. Guys, I'm going to repeat myself one more time. If they mention left and right, give them left and right. If they do not mention left and right, you have to give them left and right. And I said that before. Okay, so arbitrarily close, plug in again, look for the signs, and give them left and right always. Okay, let's see this. The graph of function g of x is pictured to the right. Often rationalization can be used to evaluate a limit analytically. Find the following limit. Now, this is my limit. If I look at the graph, I'm approaching 3 from the left and right. So the 3 is right there. This is 3. I'm approaching from the right. I'm approaching from the left. And you know the y value up here is this point. That I really don't know what that point is because I can't tell. It's not, I don't think it's half, probably 1/4 or something. I don't know. But if I use my algebraically, I plug in 3 and see what I'm getting. If I'm getting 0 over 0, I need more work, I'll plug again, and then we go from there. So let's try what are we getting here. So I'm approaching, because I can't see up here what the number is. So let's plug in 3. So I got 3 plus 1 minus 2, these two in square roots. I got 3 minus 3. Oh, okay, I got 0 here. This is 4. and square root of 4 is 2. 2 minus 2 is 0. So I got 0 over 0. Now, do you see I have a square root? I have a square root, and when you have a square root all the time, you make sure that you do conjugate. Okay, you can factor, you can find least common denominator. There is no distributive property. You can expand the function. Conjugate is the only option you have here. So I'm going to do conjugate here. Okay, so let's do conjugate. I'm going to write this question one more time. Let's see. I want to use a different color. This one probably. Okay, let's do limit x approaches 3, x plus 1 minus 2. This is in square root, and I got x minus 3. Now, conjugate means multiply this square root portion, top and bottom. But you see the sign outside the square root, not the sign inside the square root. You don't touch the inside sign, just the outside sign right there between these two. This is going to change to positive. So I have x plus 1 square root plus 2. Then I'm going to multiply, I'm going to do the same thing up here. Okay, top and bottom exactly the same. That means conjugate, if you guys don't remember in case. This is the limit x approaches 3. Now let's try and distribute. So when I distribute this square root portion, that's one term, with this square root x plus 1, then you know square root cancel out, and I'm left with x plus 1. So I got x plus 1. Now I multiply this square root with the 2, so I'm getting plus 2x plus 1 square root. Right? Do you see this? This, and then I multiply that one. It's like a distribution, like a FOIL. This is what it is. Then I'm going to go 2. We should have different color. This and this. So it means I'm going to get negative 2x plus 1. And I'm going to multiply one more time. Negative 2 with positive 2 will give me negative 4. So if you guys pay attention over here, these two cancel out. I'm left with x plus 4 minus 4. Okay. I'm sorry, x plus not 4, x plus 1 actually. This is 1. That one, x plus 1. So this is what I got. In the bottom, do you see the bottom? You're going to keep the bottom as it is. Do not ever do anything with the denominator in the AP Calculus AB class. Don't do anything. Leave it as it is. Don't simplify, add, subtract, or anything. Okay. So I have x minus 3 times x plus 1 square root plus 2. And I'm leaving this as it is. Okay. Now let's do this. Limit x approaches 3. And you have to write this over and over. Okay. No matter what. So I got x plus 1 minus 4 will give me x minus 3. Then I have x minus 3 in the bottom again. And I'm going to keep the, what is it? I'm going to keep the denominator. Like I said, we don't touch denominators. Don't simplify it. That's what I mean. Like don't multiply them together. Don't do that. So x minus 3, x minus, you can do cancellation. They cancel out. Do you see you have a whole at x equal 3? And this is what the whole is at x equal 3. When I make x minus 3 equal 0, it will give me x equal 3. And that's a whole. Cancellation is a whole, remember. So what is left? So I'm left with 1 over x plus 1 square root plus 2. Now plug in that 3 one more time, because we can't do anything else with this. 3 plus 1 is going to give me 4. 4 is a perfect square, so 2 plus 2, which will give me 1/4. See, I told you guys this was 1/4. This is 1/4. So limit x approaches 3 from the left and from the right is equal 1/4. So that's another way to figure it out. And do you guys see this conjugate thing? So this is what you're going to do. So, and you have x minus 3 equals 0, which will give me x equal 3, and that's a whole because I cancelled. Okay, so this is what it is. And if you guys have any questions, please comment below. Watch this video like 2-3 times and do the questions on your own when you see them. And have a good day, guys, and see you in the next video. If you are new to the channel, please subscribe. I would appreciate that. Thank you. Bye.